Hi class, this video is on topic D2, diffraction of interference and using water waves. So we are going to be using, I'm going to introduce you to what is called a ripple tank, which is just observing water waves to notice interference patterns. And this is going to be extended to light later in this unit. So the learning goals for this lesson are to understand and use the terms diffraction and interference, and to be able to describe the factors that affect diffraction and two-point source interference, and be able to use 3 brand new formulas for determining the wavelength given an interference pattern for mechanical waves. So there are several new equations that are coming up in this lesson and in future lessons, and they might seem confusing at first. I highly encourage you to pause this video and go fetch a blank sheet of paper, maybe colored markers, and I want you to create a formula sheet for yourself for this chapter. I want you to pause the video each time we get to a new equation and annotate that formula, what the variables mean, SI units. Maybe if you have a couple of minutes of patience, draw a neat diagram, label the variables. If you like color coding or you're willing to try it here, it can be really helpful. So let's get started. So water waves, it's an example of a mechanical wave. They behave similarly to other waves, and many wave properties that occur for sound and light can be best demonstrated, easily demonstrated using water waves because of the long wavelengths of water waves, allowing for easier observation. So what's very frequently used in physics classrooms is the setup of a ripple tank. So if you imagine a shallow glass tank of water, so there's a container that holds water, and from above, you're gonna do something to the water and shine light so that below you see the, when there is a crest, the water is deeper, so it would be a gray line. And when it's very shallow, there would be less blocking the light, so it would be a white line. Yeah, so I'm gonna link to this YouTube video. I can't show it within this YouTube video, but I'm gonna link to this to so that you can see a ripple tank in action. I have a simulation that I'm able to show here that we're going to show soon. So one of the things that a ripple tank can demonstrate is diffraction. So water waves created by a linear source will travel as a straight line as seen from the top view of a ripple tank if water depth is constant. And if the wave enters, if it encounters a boundary, it will bend. Diffraction is the bending or spreading of a wave when it passes through an opening. And the amount of diffraction depends on the wavelength of the waves and the size of the opening. So here, these 2 diagrams demonstrate the first point of this bold, important statement. A short wavelength would have a certain amount of bending of the light, a certain amount of diffraction, and if you use a longer wavelength water wave, then you get a greater degree of diffraction. So let's just expand into that bold statement because it is an important learning goal of this chapter. What affects the amount of diffraction? Let's compare the 3 diffraction patterns with the same opening width. So just before in the previous slide, we looked at the effect of different wavelengths. Now we're gonna look at, we're gonna look at, 3 different wavelengths, but the actual water waves, so these are photos, not graphics, so you can see it to believe it, with the same opening width. So notice this opening right here is the same width, but the waves that are incoming, so the source is at the bottom and the wave front is here, and it's traveling, the wave ray is that way. So we've got short wavelength, larger wavelength, and larger wavelength. So notice how the diffraction is different. As the wavelength increases, the amount of diffraction increases. Waves with shorter wavelength diffract less than waves with longer wavelength. This is why bass notes travel better around corners. So if you were to hear a music blaring from like a car or in the distance, chances are it's a bass note because of for one reason, that those longer wavelengths are better able to diffract. And then just continuing what affects the amount of diffraction, compare the 3 different diffraction patterns using the same wavelength. So before we had the same width opening and changing the wavelength. Now we have the same wavelength but different opening sizes. So here we have wide opening, and this time the wave source is on the left side, so the wave ray is coming to the right. So when we have a specific wavelength and the width is very big compared to that wavelength, there's nearly straight line propagation. They're almost parallel lines. They're just slight curving on the sides. It's a really, if there was a radius of curvature, it's a really big radius. Oops, where's my slide? Big radius of curvature. Now, if you have the same incident rays, the same wavelength going into a much smaller opening, then there's going to be a lot of diffraction. So it's very circular. And then if you have a very short wavelength compared to the slit opening, then you have a lot of diffraction. Noticeable diffraction occurs. So you could just think of diffraction occurs when the wavelength is comparable to or greater than the slit width. So lambda is our established variable for wavelength, and it's bigger to or equal to W, which is the slit width here. So if we go back to here, we're looking at this distance here from crest to crest compared for lambda versus this for W. So it's okay if W, it's okay if, I think I got that backwards. Noticeable diffraction occurs when wavelength is comparable to or greater than the slit. Just going back to this slide, I just want to re-explain this. Look at these 2 diagrams. Compare these 2 diagrams where there's the exact same wavelength and different width. When lambda is much smaller than width, we do not get noticeable diffraction. However, when lambda here is the same size as width, or even if it was like much longer than the width, then we get significant noticeable diffraction. This third diagram is putting those 2 things together. So you've shortened the wavelength and the slit was smaller than this one. So a small width. Okay, let's go back to this slide and try this again. So here and here we have the same wavelength. When the width gets smaller, you get more diffraction. From this diagram to this diagram, the width was the same. And if the wavelength got smaller, then you get less diffraction. So the 2 things that give you more diffraction are a longer wavelength or a smaller slit width compared to the wavelength. And there is I guess the defining point where you can see noticeable diffraction or not is when they're equal. So lambda and W being equal would give you noticeable diffraction. And then if the wavelength is even longer than that, you get even more diffraction. So further, if we think about the bass notes having which is another example of mechanical wave. So the bass notes of sound having a very long wavelength, then there's lots of diffraction, which is why you would hear them travel from room to room. Okay, let's try an example. A water wave with a wavelength of 0.75 meters passed through a 0.25 meter opening between two fallen lots will diffraction occur. So we have a water wave with a wavelength given. So this is lambda, and it passes through a certain size opening. So that's W. So simply we just compare, write out our givens, compare. Wavelength is bigger than W, therefore diffraction is noticeable. Okay, so far we've just been talking about a wave, a single wave. Now let's talk about interference. So often a wave meets another wave. Like if you have two separate sources, like two different speakers set up on opposite corners of a wall, or even more often when a wave meets itself after a reflection. Or when a wave goes through two openings and each of those openings looks like a new source. And then there's going to be curving and diffraction, and those two apparent sources may interfere with each other. So we're just going to recap the principle of superposition, which applies to wave interference. So remembering from last year, when two waves meet within a medium, they will pass through one another. The resulting displacement of the medium at any location is the algebraic sum of the displacements of the individual waves at the same location. So imagining this crest maybe going to the right and this crest going to the left. At the moment that they overlap, they will, I guess this is partial overlap. So at this moment in time, if you have them separately, they each look like that. But if you have them together, this piece will stack on top of that piece there, and you'll get the principle of superposition. If you had a pulse going to the right and a pulse going to the left, at the moment that they were overlapping this way, then you would see that triangular piece stacked over top of this rectangle. So it's the algebraic sum. And interference is the phenomenon that occurs when two waves in the same medium interact. And the interference is coherent when the two waves have the same frequency and fixed phases. And when those two waves cross paths, they become superimposed and they interact in different ways. So it can be constructive or destructive. Constructive or destructive. So just taking a look at a bigger view of that diagram for constructive interference, we have a crest and a crest adding together to form like a super crest. If this was an amplitude of 1 and this was an amplitude of 2, this would be an if this was 1 and this was 1, then this would be an amplitude of 2. This crest plus this crest would be an amplitude of 2 as well. So we get constructive interference where the amplitude increases. This constructive interference happens when the waves are in phase with each other. So notice that the crests line up, the troughs line up. Every node on the way up lines up with nodes on the way up. And destructive interference occurs when a crest meets a trough and a trough meets a crest, and at all points, the algebraic sum is 0. This is perfect destructive interference. This happens when waves are a half a wavelength out of phase. So if you think of this situation here, how would we have to shift so that this trough lines up with that crest? It's a half a wavelength away, whereas the full wavelength is there. So you'd have to shift it by that amount. So a half a wavelength shift, because the waves look like trig functions, sinusoidal functions, sometimes we say it's 180 degrees out of phase, because in a sine function, one full cycle, unless you're doing transformations on sine theta, y equals sine theta is, one full cycle is 360 degrees. So 180 is half. So that was, you should have learned constructive and destructive last year, but just to clarify, it's when the crest and the crest meet, the resulting wave has a higher amplitude than any individual wave before the interference, and the destructive interference occurs when the crest and the trough meet, and the resulting wave has an amplitude that is less up to, taking away up to all of it. So it could have an amplitude of 0. The conditions required for interference, we must have, for this interference that we're about to talk about today, you must have 2 or more waves moving through different regions of space over at least some of their way from the source to the point of interest. The waves come together at a common point. So it's like, where do they bump together? And then the waves must have the same frequency and a fixed relationship between their phases such that the phase shift is constant over time. And waves that meet that condition number 3 are called coherent. Okay. So do you have your formula page ready? I'm not going to ask you to draw this. There is a simulation, but there are formulas that are coming up based on something that may look like this. So, interference patterns for 2 point sources. So remember from the last video, there could be a point source or a linear source. So we're talking about point sources, like you're dipping an eraser in, or there's a dropping of a pebble into the water at this point and this point, or maybe this is a speaker and this is another speaker. S1 and S2 are point sources, and they're continuous waves, so it's whatever is in the water is bobbing up and down, or the speaker is going to constantly play that note. There's the same frequency and amplitude from each of these waves, and they are in phase with each other. So that means if the two rocks touch the water at the same time, and if the rocks were lifted up out of the water, they'd be lifted up at the same time and down at the same time. So solid lines, recall that's the crest. Those are the crests, and the dotted lines are the troughs. The wave fronts are here and here. And the wave fronts are circular because we're talking about point sources, not a linear source. And then there are many places where a crest, a solid line, meets a crest of the other wave. And when a crest meets a crest, that's constructive interference. So in this diagram, a constructive interference point is a solid dot. And then destructive interference, where a solid line meets a dotted line, is a hole. And you can see there's a pattern of constructive interference that forms these curves. And the same for destructive interference. So we have destructive interference line, constructive interference line. Destructive, constructive, destructive, constructive, destructive. We've got the midpoint, and then that's constructive, and then we got destructive, constructive, destructive, constructive, destructive, constructive, destructive. Okay. So these lines of destructive interference are really important based on what we can see when we actually do this as an experiment. And we'll talk about why you might want to do this as an experiment. Oh no, this is supposed to be a GIF. Oh no. Okay, I just asked Fia out loud for help. I think that's what people do in quarantine. They talk to their pets now. Anyway, she solved it. Fia to the rescue. So you see you have 2 point sources, S1 and S2. I wish I could slow this down, but we'll just watch it again. So the red lines represent points of constructive interference, and we use M for those. The blue dots represent nodal points. That's where we have destructive interference, and we're going to call those N, despite the labeling of the physics classroom. They have their own notation, but we are going to call the nodes, we're going to call the nodes by N equals 1, N equals 2. Okay, let's take a look at this again. Hopefully it will start up. Maybe I can do this and force it to. Okay, notice the crest and the crest meeting. When the colored dots come up, notice it turns into a red dot because it was a solid line and a solid line. And then also notice when the thinner lines, which are the troughs in this case, there's also a pattern. These are called the nodes. Okay, we're not going to use their numbering system, but I do like it that it's like a little animation. So these lines are symmetrical. So these patterns spread out from the sources, producing these line locations where there's constructive or destructive interference. And a node is a place where destructive interference occurs. That's when the crest of +1 is adding to the trough of -1 and giving you zero amplitude. And this pattern includes, they're alternating. So it's destructive, constructive, destructive, constructive. And the lines of zero displacement, so the lines of those nodes, are called nodal lines. And how you would actually see this, there's a little simulation, I think, that I've put in here. And so if these were two water waves, how would you see the areas of constructive interference? So these lines with a solid dot. It would be really distinct black and white, or like very dark and very light. More distinct than these dark and light because the amplitude is greater. So it's like your water level is really high here. Really high or really low. So you get, I'm going to show you this. But the destructive interference, that's where you have zero amplitude. So it's kind of a fuzzy, I call them fuzzy gray lines, these destructive nodal lines. And I'm going to show you what I mean. Oh, happy birthday to anybody who has a birthday coming up. Okay, so for 2-point source waves with the same frequency and amplitude, actually, I think I'm going to take a moment right now to go to that simulation. So let's go to the simulation. So there is a FET for this, and I'm going to put the link in the bottom. So it's great. And you could click on different kinds of interference. So there's just waves, interference, slits, or diffraction, and we are going to get to some of these other things. So let's just start with one wave. So we've got a faucet that is dripping. And so that's what crests and troughs look like for the one wave. And if we turn on the second faucet, and hopefully it's going to drop at the same time so they are coherent, you can see we get these two nodal lines. So that's what I mean, they're like gray fuzzy lines. And this is where it's really bright and dark. So now if we were to change the frequency, anyways, you can play with this to see what would be the differences. Oops, play. We can play with the separation. You can play with the frequency. So there's a few things you can do. You can make them speakers or drops of water. So pressing play. Okay, pressing play on the droplets. Maybe there was meant to be sound. Oops, it reset again. So you can see here when I changed my settings. We're going to talk about changing settings for changing the interference patterns, but do you see how the number of nodal lines, those gray fuzzy lines, those areas of destructive interference, that's really what you could draw a line and measure and do a calculation with. You can't really distinctively see the areas of constructive interference that well. Okay, I think we've had enough of that. But anyways, that's a FET that I encourage you to actually go into and change settings to observe. So here's where the calculations come into play. So for 2-point sources with the same frequency and amplitude that are in phase, the nodal lines are destructive interference. the lines form what's called a hyperbola, or each line is a hyperbola, and their pattern is symmetrical about the right bisector. The right bisector, so the word right means 90 degrees, so, and bisector means it cuts in half. So what does it cut in half? There's a horizon that connects the two sources. And if you were to draw a line between the two sources, cut that line in half and then draw a 90-degree line up. So that would be the right bisector. And if you, so let's say we did an experiment, you would take this, this black and white, you would draw on the fuzzy areas a nodal line, and then you would number these lines, starting from the right bisector, then it would be n equals 1, n equals 2, n equals 3. There was a previous GIF that didn't use this numbering system, but note that this is our numbering system we're going to be using with our equation. So make sure you follow this. And if you don't know what a hyperbola is, so it kind of sounds like, or it looks like parabola. So it's just, similarly, it's just a mathematical curve with certain geometric properties. They've taken hyperbola out of the high school math curriculum, but maybe some of you know about it. So there are certain geometric properties. The textbook uses these properties in order to derive equations for the different features of this two-point source interference pattern. So let's now talk about, if I were to go back into my simulation, if I were to increase frequency, what would happen? So from here to here, the only difference, so notice the separation is the same. So the only difference between these two different diagrams is the frequency. When we increase the frequency, the wavelength decreases, the nodal lines come closer together, and the number of nodal lines increases. So you can see maybe 1, 2, 3, 4, 5, 6, 7, 8. And there's many more than 8 here. What happens when you increase the distance between the sources? So here they're closer together, and here they're farther apart. When the distance between source increases, the number of nodal lines also increases. Okay, so I guess an important question is why? Why would we do this? So we would set up an experiment, like maybe a water wave experiment, and we would take a picture of the interference pattern, draw out those nodal lines, and why would we do that? So for water waves, this would be just sort of like for practice, because we can easily determine the water wavelength because it is, it's pretty long. But if we're talking about like light or other waves on the electromagnetic spectrum, so not mechanical waves, electromagnetic waves, we can't determine the wavelength very easily, but we can do an experiment with light or water. We can take a picture of the interference pattern. You can draw your nodal lines, and you'll be able to calculate the wavelengths of the sources. Okay, so getting into equations, source 1 and source 2 are called S1 and S2. They are 2-point sources, and the purple horizontal line joins the two sources. So here's our horizon. I mean, I call it horizon. It's not an official name. We've got our horizon, and then we're going to take the distance between point 1 and, source 1 and source 2 on the horizon. We're going to cut that in half, and we get the right bisector. So that blue dotted line is the right bisector. Then we're going to draw out our nodal lines and pick a point on the nodal lines. We are going to connect that point on that nodal line with S1 and S2. So this is called P, this is called S1, S2. The nodal lines on either side of the bisector are labeled N1, N2, and so on. And on the right side are labeled points P1 and P2 located on N1 and N2. So we've got P1, P2. So the number that goes with P is based on which nodal line it's on, it starts from, and then the line to source 1 would be S1. And the length of this line would be P1S1. And the length of this line would be P1S2. And we do the same thing for P2. Lines are drawn to connect the source locations to these points, P1 and P2, and they are called path length. We have an equation for the difference in the path length. So how much longer is this green line than that green line? So the difference between those two lines is a special formula. So the magnitude of the difference is equal to the nodal line number minus 1/2 times wavelength. So we can rearrange this for wavelength, which is often what we're looking for. So pause this video, make sure you draw out your little diagram, your formula. So whatever nodal line you're on, that's going to be your subscript for P, and you have, it's a 2-point source pattern, so it's going to be S1 and S2 all the time. I'm encouraging you, when you're doing problems like this, you don't have to draw all these black and white circles and the interference patterns, but you want to label S1, S2, P, like 2 or whatever it is, and then you're going to want to have this triangle there just to help you visualize what it is we're doing compared to the experimental results and the math. So let's try an example. 2 identical point sources that interfere in a ripple tank are 5 centimeters apart with a frequency of 8 hertz. A point on the first nodal line is located 10 centimeters from the first source and 11 centimeters from the other source. Calculate the wavelength and speed of the waves. Okay, so you want to look at our brand new equation and see what information we have. Probably drawing a diagram. So drawing a horizon like S1 and S2, then you're going to draw your right bisector, and you see a point. So you can just draw it somewhere in the top right-hand corner. That's the point that we're talking about. It says the first nodal line, so you can call that P1, and the distance between that and one source is 10. The distance between that and another is 11. So do you see that this is P1S1, P1S2? So let's write that up. So I've drawn my diagram. I have S1 and S2 labeled. I have P1 labeled. We've got 10 centimeters on the shorter side, 11 centimeters on the longer side, n equals 1. So in this formula, we have everything except for wavelength, and we can solve for it. P1S1 minus P1S2 divided by 1 minus 1/2. And we get 0.02 meters. And then taking a look at how many significant figures we need, it looks like 2. Oh, we actually did not use that number, so we're going to look at all the numbers we actually used. So 3 sig figs, 3 sig figs. We didn't need the frequency. We didn't need the source separation. And so 0.0200. So all of these 3 numbers are significant figures. And then the second part of the question, it says, what is the speed of the wave? That universal wave equation, universal should tell you that it's useful in a lot of different questions. V equals F lambda, and we can solve for our speed of 0.16 meters per second. Okay, let's go back to our slides. So we have this first equation, which is the relationship between the path length difference and the wavelength. But the problem is that if the point that you have is really far away, if the points are really far away from the source, there's not going to be much difference in the path length. And sometimes wavelength is too small, method 1 won't work accurately. So sometimes when you get your experimental data, you might try that equation and it's not going to be accurate. So there's another solution. So if the problem was that your point was really far away, if you notice that the further away it is, the more those lines look parallel to each other. And if they actually were parallel to each other, we could form this triangle here, and we could have a relationship between the distance between the 2 sources and the angle that the nodal line makes with the horizon, well, I'm calling it the horizon, with that horizontal line. We know, yeah. So the textbook derives a new equation You still have the n minus a half, but it's lambda over d on this side, and it's sine theta n. And theta n is the angle for the nth nodal line, and d is the distance between the two sources. So the derivation has a diagram that looks like this. You've got the point is so far away, they look parallel, and then you've got this triangle here that if they look so far away that they're parallel, then there is like a 90 degrees in there that through, I can't remember what it's called, complementary angle? Anyways, you can work out the angles to get theta n, and it's sine theta n equals this over d. Yeah, so we've got, we can use SI units of meters for this equation. Okay, so the bad news is that sometimes our angle is too small to use that equation, and method 2 won't work accurately. So another, a solution to that allows us to come up with equation number 3. So using similar triangles, we can find that the following is true. Sine theta n, which is this angle here, is equal to xn, which is the distance between that right bisector, the 90-degree distance between the right bisector and that point, and the length there, the direct length between the center point here and there. Notice this is not PS anything. That would be P1S1, P1S2. So this is a different line. There's so many lines. I hope you are color coding your formula sheet. So we have xn over L, which is the perpendicular distance from the right bisector to the point, over the length of the line from the midpoint to the source of the point, equals n minus 1/2 times lambda over d. And d is, again, the distance between the two sources. Okay, let's practice that one. Between these 3 equations, you might wonder, well, how do I know if I have that problem that led to the next equation? You are just going to look at the given information in this problem. If we actually do an experiment, you would have to judge whether you have one of these 3 problems and which equation is going to be the most accurate, or sometimes in experiments, you're going to calculate something experimentally, like 3 different ways, and you're going to report all of them. And maybe there's more information that helps you decide which one's most accurate. So in this example, we're just going to look at what we have and pick one of the 3 equations. So the distance from the right bisector to a point P on the second nodal line in a 2-point interference pattern is 4 centimeters. The distance from the midpoint between the 2 sources, which are 0.5 centimeters apart, to point P is 14 centimeters. Calculate the wavelength. So the first phrase to highlight, 2-point interference patterns, that phrase directs you to one of these 3 equations. Then you see the distance from the right bisector to point P. Do you recognize the phrasing and which variable that is? The distance from the right bisector, oh yes, we're gonna draw a diagram first, draw the 2 points, that horizon or horizontal line, and then the right bisector. The distance from the right bisector to point P is 4 centimeters, so that's X. And then the distance from the midpoint between the 2 sources, that's this point, to P is 14 centimeters. And then the distance between the 2 sources, that's 0.5 centimeters, that's D. So we have those givens, and we can just, it's a simple rearrangement for this equation, and you just plug into the equation, and we get 9.5 times 10 to the power of, oh dear, I'm not sure why that didn't show up, but let me just quickly calculate it. So it should be times 10 to the minus 2 centimeters. 9.5 times 10 to the minus 2 centimeters. Now, this is truly what the nodal lines would look like. They would be hyperbolic like that, but you don't really need that diagram. What you need is a diagram for this that fits this equation that shows that triangle there. So you don't see the wave fronts, you don't see the nodal lines. You're just going to highlight, that's how I do it. I isolate those quantities because it otherwise gets too messy to draw all the nodal lines. Okay, so we've done a couple of examples. We've learned 3 new equations. We've gone over diffraction and factors that affect diffraction. We've gone over the 2-point interference pattern and factors that affect it and our equations to analyze it. So now it's time for you to practice. Make sure you fill out the exit ticket for this video, video D2, and submit your practice questions. And don't hesitate if you have questions on this material. Have a great day.